Thanks. It's always great to be back here. I was here for a year, like at Princeton. It kind of feels like home every time I come back. It's a really good feeling. All right, so I'm going to talk about this joint work with Yuval Filmus, my student Liana, my brother Priya, and his advisor David Zuckerman, his postdoc advisor. Okay, this is like as soon as I sent the abstract, I realized it's going to be a difficult thing to talk about. It's kind of technical, but there are a lot of new ideas in this work, so I'm going to try my best not to make the talk very technical. But let's see how I do. It can be also notation heavy. But all right, so let's see what we want to do. We have a Boolean function, f from 0, 1, n to 0, 1. Let's think of this as a voting scheme. I think it makes the language simpler to talk about. And I'm going to assume that the function is kind of balanced. So that f is balanced or almost balanced in the sense that it's not, its average is not very close to 0 or very close to 1. So if you want, you can assume expected value of f is half over a uniform distribution, or something milder that is just bounded away from both 0 and 1, so in some range. So it's not very biased already. So what we want to understand is, well, I'll talk about influences, but I'm going to interpret them in this way, that can a voter or a collection of voters where they form a coalition influence the outcome of this election or this voting towards a particular value. All right, so this is what we think of as the influence of them, right? Like a voter, how much can it influence the outcome towards a particular value? Or if we form a coalition, how much they can collectively influence it.
You didn't say it explicitly, but every variable is associated with a
voter. Exactly. So every variable is a vote of a person. So we have two candidates, by the way, 0 and 1. And we have n voters. Each one casts a vote, 0 and 1. And for now, like in the beginning, let's assume they are casting their votes randomly. So they flip a coin with probability half, it's 0 and 1. But we have some candidates that they want to influence this towards a particular value. So that's so let me define the notation here for that. So I'm going to denote this. Maybe it's not such a great notation, but let's stick with it. So the influence towards a value b of a collection of voters S on F is the following. So we pick some voting, so x at random. And then what is the probability that this coalition can cast their votes in a way that the outcome is b? So what I want is that f of y to be b for some y such that y matches x on things outside the coalition. So the way I want to think about it is that as if everybody votes, but then the coalition can change their votes, which is the same as everybody else votes and then the coalition votes. But they can look at the vote of the other people. So you can think of it as this is the non-coalition part of the vote. So xs bar. So these people first vote, and then the people in the coalition, xs, they vote second. So they look at the previous votes and decide their best possible way to. So they're kind of adversarial. They act it in an adversarial way. So another way to think about it is, outside this voting scheme, is that, so you can think of it as a source of randomness. It's generating a random bit for us, which is a good random bit. It's either perfect or almost perfect. It's not very biased. But we have these adversaries, and this randomness comes from n sources, right? So it looks at these n bits, which are supposed to be all perfect random, and gives us one bit of randomness. And we want this to be resilient against adversarial attacks, that we don't want to have a small coalition that together they can really influence this outcome towards a particular value b. So suppose they want to destroy this unbiasedness, make it almost always 1 or almost 0, or just like whatever works for them. So this is the resilience thing that comes up. It's another technical term that's used here. We want to say the protocol is resilient against coalitions of certain size, meaning that there's no small coalition that can make it really biased. OK. So when you talk about influence, you have to mention, I mean, the first thing you mention is this.
Maybe
yes.
want to say that if F was parity, that's the worst thing to do. Everybody has.
Yeah, exactly. So I'm going to go over 3 examples like in 2 minutes. But yeah, like in the parity case, for example, even a single player, you look at the vote of everybody else, and then you can just change the outcome to whatever you want, right? So it's the least resilient function you can imagine. All right, so there's a theorem here, KKL, due to this is order Kahn-Kalai lineal, that they show there's always an influential variable. So they show that there's a single voter always, so there exists some I, such that they can influence it to whatever. I mean, here it's going to be symmetric. So the influence of this variable towards 1 is large. So you're going to gain something here, which is 1 plus this omega of log n over n, which actually is equivalent to saying that the influence also towards 0 is at least. So there is an influential variable. There is a single voter where they can she can change the outcome by log n over n towards any value that she wants.
So 1 over n would have been
yeah, one.
Proportional influence.
Exactly. So 1 over n is the obvious lower bound for something like that, because the sum of these influences is going to be at least the variance of f. But the trick here is to get something over 1 over n, and they gain a log n over that. So that's a non-trivial, highly non-trivial result, and it's a very interesting result, not only because it's very important, also the proof. It's I think it's the paper that brought these techniques from harmonic analysis, hypercontractivity, at least that technique, to the discrete math and theoretical computer science community, and then people started using it, and now it's really a common tool in many problems. All right, so yeah, we have this.
Does this imply that a coalition of n over log n voters can somehow bias the function by a constant?
That's my next. Exactly. So what it implies, that's answering that question, is that it has a corollary, which is actually more relevant to what I'm going to talk about, is that, so what can we do? Suppose instead of, here we just gain log n over n, but we want to really mess up the biasness. We want to really influence it towards, say, 1 or 0, make it really close to 1 or 0. What we can do is that, suppose we decide we want to make it close to 1, we pick one variable, which is influential, so it gives us log n over n. We pick another one, so we continue doing this. As long as we are still far away from 1, we KKL holds, so we can find such variables. So we can go really close to 1 if we want, the average. Or we can go really close to 0, but it's going to be a different sequence. Right? So if you are going through 0, your first voter is the same, but then the second is going to change, because now you're going to set this to 0, to the correct vote, and continue like that way. So the corollary that we get is that there exists S1 whose size is at most, let's say, big O of n over log n. What really I care about is little o of n. So this is a small compared to the players. Little o of n, such that they can really influence f towards the value 1 minus epsilon. And this constant here is going to depend on epsilon. The same thing with S0. We can do the same thing towards 0. Okay, but then they don't need to be the same collisions. And it's not true that you can always pick the same.
And this holds for any measure that's balanced?
No, so that's going to be what I'm going to prove. So at the moment, I'm only talking about uniform measure.
Okay, I didn't
So
see that on the board.
yeah, so I should have written really. Right. I mentioned it verbally, but that's right. So here I'm assuming this is uniform. Right. Yeah, it's actually these two statements are equivalent, because you can add them up and just like if a voter can influence this one up, then automatically the other vote is going to bring this one, the chance of 0 down. So
It's just a probability that the value of the function is not fixed by the remaining.
yeah, I defined it a little bit.
It's the same person who can influence both 1 and 2.
Yeah.
Yeah, exactly.
It's equivalent to saying that it's a probability that all other voters except for I did not determine the value, and then they can.
Yeah, that's why I was saying maybe this is not a great notation, because normally you define the influence by the difference, how much you can influence. So this log n over n is usually the right notation. It's like the derivative.
In the corollary, are the two sets the same?
No, that's not they are not the same. Because the thing is, like when you want to prove the corollary, you fix the vote of this voter, then you're dealing with a different function, right? Because you're restricted to this value. So you get different voters. So let's look at some few examples to kind of warm up about this. Because if you don't warm up, you might get injured. So majority. So here f of x is just 1 if the sum, or let's say if and only if the sum of xi is at least n over 2. So this is just the central limit theorem, or the concentration bound, basically. So here we can take S0 and S1 to be the same S, which is just any set of roughly, so let's say, put a square root n with some big constant, I think over epsilon, let's say, voters. Right, if you pick, I mean, we know if you set square root n of the votes to 1, then suddenly the expected value shifts by a constant, right? And if you make it a little bit larger, instead of square root n, put 100 square root n, then it's going to get really biased towards 1. If they all vote 0, it's going to be, it gets biased towards 0. It's going to be very unlikely that the average is going to pass n over 2.
And if they don't even have to look at what the other.
Yeah, exactly. So they don't have to really look at, they don't need to take advantage of the fact that they can look at the other votes. Actually, that's the case for all the monotone functions. If you're dealing with an increasing function, if you want to go close to 1, you have to vote 1. There is no advantage in voting 0. And if you want to make it close to 0, then you have to vote 0. So this advantage that we have here, that they can look at the other votes, really comes into play when the function is not an increasing function. It's not a monotone function. So right, so in this case, we get square root n, which is some win over this. The second example, which is the example that shows KKL theorem is tight, is tribes. And in this example, so what is this function? It's the OR of n's so we put our variables here separately, so x1, x2, and these are log n roughly. So these are log n of these, and this one is n over log n of these. So we divide them into different tribes. That's where the name tribes comes. Each tribe is of size log n. So this is a different tribe, another log n of those. And we take and of each tribe. So they need to basically get, in order to vote 1, they have to have a consensus. All of them should say 1. And once they vote 1, we want at least one tribe to vote 1 to get for the 1 to be elected. So that's OR of a bunch of ands, or max of a bunch of mins. So what is the situation here? For S1, in order to make the vote 1, the outcome 1, I just need to have one full tribe vote 1, right? So I can take S1 actually to be log n, of size log n, and that's one full tribe. What about S0? Here I need to take, having a few tribes voting 0 is not going to really change much, because most tribes actually, with high probability, they're going to vote 0 anyway, because they need the consensus to vote 1. So here we really need to make sure many tribes vote many more than what you expected to vote 0. So here I can take n over log n actually. Just take one agent from every tribe, and they vote 0, right? Right, if I take one member from each tribe, if they vote 0, all the tribe votes going to be 0. The outcome is actually exactly 0. Here also the outcome was exactly 1. So we see here the difference actually. You can't do really much better than n over log n for S0, but for S1, a small set works. And then the parity example, as Avi was mentioning. So here f of x is 1 if and only if sum of xi is 0 mod 2. And in this case, you can take just a single voter. So S0, S1, just S. They need to be just contain one voter. And this is not a monotone function, so the voter has to look at the outcome of the other ones. But it just adjusts it to fix the parity to the value he or she wants, right? So everybody votes. If she wants the outcome 1, just votes whatever value fixes the parity to 1, or 0, the same thing. So just can contain one voter. So this is the least resilient function, basically. It's not even resilient against voters of size 1. OK, so now, so these are the uniform case. So the uniform case is kind of understood to some extent. There are some conjectures there, but at least this kind of things are very well understood. The techniques are really, they all come more or less from KKL, so it's Fourier analytic. It looks at these high frequencies versus low frequencies, so it's kind of a spectral technique in a sense.
Do you know an example where n over log n is needed for both S0 and
No, I don't.
But almost, yeah, we know n
Oh.
over log squared is linear.
Yeah, exactly.
And
Right.
it was made explicit more recently. But anyway, it was an existential proof, probabilistic function, but then, just Faraday and Zuckerman.
Yeah, exactly.
But Rumeka have really explicit functions
Yeah.
which achieve resilience in both directions against n over log squared.
Okay, and n over log square n is
Yeah, so there's a log n.
No, it's open between n over log and n over log squared is open.
Yeah, it might be the case, but it's open. But there's exactly just a small gap left there. So what I next want to talk about is, so this talk is about generalizing this to more general measures. So the first attempt to this claim that actually they can do it for all separable measures, basically, but which is equivalent to the continuous cube. There's a funny story here too. So this paper Bourgain, Katz, Nelson, Kahn, Kalai, Lineal came out, I think, a bit after KKL. So they proved, or they gave a proof, I'm not sure, it's called proved, and also at the same time provided a counterexample to the same statement in the same paper. So they claim that this KKL corollary that I wrote about is true for functions over continuous cube. So interval, real interval 0, 1, 0, 1. And again, this is with the uniform measure, like Lebesgue measure. Yes, so this is equivalent to saying alphabet size n. So you can discretize it, divide it into n intervals, so that gives us enough accuracy and error.
Same n is in the exponent, like the dimension?
Yes, exactly.
Oh, the same.
It's the same n, yeah. Yeah, so you need that much accuracy when you discretize it, so you can think of it that way. So they claim this is true, but not true, really. So there's a counterexample, which is in their paper. So what happened here is, I'm being a little bit unfair. So what they proved a version of KKL, which with a different notion of influence, which I'm not going to talk about. And then they kind of like very sloppily said, OK, so now that we have the KKL, we can get, of course, the corollary. But this other notion of influence doesn't work in that way. So you can't just fix coordinates and apply it recursively. So let's see what is the counterexample. It's fairly simple. So the counterexample is, we can say f of x is 1 if and only if for every I, xi is at least 1 over n. So it's like this and version.
1 minus 1 over n.
I think 1 over n. Whatever.
You want it balanced.
For every I. So it's like 1 over e.
Yeah, very good. Yeah.
Yeah. So here, what is expected value of f? The probability that f is 1 is exactly, you want 1 minus 1 over n. That's the chance that xi is at least 1 over n. But you want this to be true for every n. So this is roughly 1 over e. You can adjust it to make it half if you want by just changing this 1 over n to log 2 over natural logarithm of 2 over n. But I mean, this falls here. Right, so it is a balanced function. But note what happens here is that it's very hard to make this function, the expected value, close to 1, because most variables are already like satisfying this condition, right? Like the chance that you are above 1 over n is very high. So if you pick a small coalition of voters and they vote something above 1 over n, it's really not telling us much because it's already kind of happening in reality. So let's do the math actually instead of just hand waving. So for every s, if the size of s is small, so it's little of n, any little of n actually here, what is the influence of this coalition towards 1? So obviously what they need to do is they have to vote, say 1 or anything above 1 over n. It's the same thing, right? So they want to vote large values. So then what is the probability that we get 1 is that the rest of the voters, they satisfy this condition. So that leaves us with n minus size of s, right? So the size of s, we we forced it because they're adversarial, they can do it, but the rest is still random, so n minus over s is still random. But this is, we didn't really gain much. This is still 1 over e, right? There's not much difference between n or n minus n over log is n or anything here. So we really need to have a big chunk of this n to be able to influence it towards 1. So it's very hard to influence this function towards 1. But on the other hand, so that's a counterexample. It shows this corollary doesn't hold. You can't find S1 and S0. But there's something interesting happening. And that is, right, on the other hand, it's very easy to make this thing influence towards 0. Just a single voter, S of size 1, satisfies a single voter can make sure that the outcome is 0, just votes 0, let's say, or anything less than 1 over n. Right, so maybe the conjecture can be salvaged, and there's this conjecture now. So I'm going to replace this with a conjecture. I thought this is due to Friedgut, because I think in print it appears in a paper of him. But David was saying Nati had asked him that conjecture earlier, before that paper was published. So I'm going to attribute it to Nati Lineal and Ehud Friedgut. So this is a conjecture. It's from 0, 1. Then we can find a coalition that can break the balancedness, but towards some value. So size of S is little of n, such that one of these things is good. So either it can influence it towards 1, or it can influence it towards 0. So unlike this discrete uniform case where we could find 1 for 1, 1 for 0, we know we can't find 1 for both, but maybe there's always at least one of the cases is easy to be influenced towards too. So I'm kind of so this is a problem I saw when I was doing my master's or maybe early PhD. I really like it because there's no assumption really, right? Like you just have a function f. We don't know anything about it, and the statement is fairly simple. You just want to fix some coordinates to make the expected value to go towards the value. But it's still open, and I thought about it at the time for a bit, forgot about it, and again thought about it, but still, like, yeah, it's kind of annoying me that it's still open. Yeah, I wanted to say that's very unusual, but there are a lot of people doing complexity theory here, so I'm sure they're so used to simple statements which cannot be solved easily. Okay, right, so this is still open. Actually, before continuing, let me say something. So in this corollary, in the KKL corollary, what is really interesting to me is that this is little of n. So I don't really, so let's forget about that we can actually get an effective bound, which is almost tight, n over log n. Let's just talk about little of n. The proof is weird, right? Like it's a spectral proof. It uses Fourier analysis. Can we prove this little of n with a simpler proof, maybe Ramsey theoretic proof, something very different? Maybe that would help us to prove this one. Because, I mean, the technique of KKL really doesn't generalize here. It really fails. So maybe if you can find a more combinatorial or, I don't know, more Ramsey theory type, like a soft proof and a soft analytic proof, like go to compactness, something like that, maybe that can be generalized. So I find it really interesting if someone can come up with a very different proof for that. Okay, so what I want to talk about now, like the results I want to mention. So what we did is we looked at something in between, which is just general product spaces over just binary 0, 1. So So I'm looking at these product of Bernoulli distributions, basically. This could be anything, mu over. So note that the counterexample still survives in this setting, right? It's really coming from that setting. For the so-called p-bias distribution, which is the Bernoulli distribution with parameter p for every coordinate. Distribution with p equals 1 over n, which just means that the probability of xi equals 1 is 1 over n. We can look at f of x is 1 if and only if x is all 0 vector. Then right, so then that no small set can influence this towards 1, because again, more coordinates are then no small, or let's say all small s satisfy.
Is p less than 1 over n the only sort of non-trivial case here? Like, for example, if p were 1 over little of n, is it easy?
No, it's still no, actually it becomes easy when p becomes roughly 1 over polylog n. So below that you can still look at threshold functions and so on. Right. Yeah, p1 over n is actually not so hard because it's very sparse. Like the support is really just a constant number of coordinates, so you can deal with it differently. So so the counterexample works here. So this is kind of a good intermediate step towards linear Friedgott because you see what fails and we have what fails there. But there now we can prove the conjecture in that setting. So this was, so the way this started, Puya was visiting Simon's for one of the workshops, and he asked me the problem that, actually it was David's problem. So David had asked this question for product spaces over 0, 1 to the n. So it wasn't really an open problem of David. And then we started working on it. It was related to things that I was working earlier. So in the end, we managed to solve it. But so the thing is, what I want to say is that there's been a lot of work generalizing these KKL stuff or related stuff to other product spaces, p-bias spaces. But they all kind of look at the techniques and they generalize the techniques in a way. Like they look at the generalizations of the techniques. Like hypercontractivity, some version of it holds and it gives us different bounds. But here, it's going to be a very, very different approach. So basically to prove this, which let me write, what we prove, we had to really reinvent a completely different proof. So it's very interesting because the proof is really different from KKL proof, and it doesn't handle KKL case. So you have the uniform case or almost uniform case. You have to do the Fourier analysis to the best of our understanding, and then you have these small, very biased coordinates like this p equals 1 over n, and for that we do something very differently. And none of the techniques handles the other case. So So this is what we proved. Mu, any product distribution on 0, 1 to the n, then there exists S. Size of S is little of n. Actually, we don't lose much, so you can get the same bound that comes from KKL. We lose a factor of log n, which doesn't really matter much, such that either this coalition can influence the outcome towards 1 or influence it towards 0. Like exactly the statement of linear Friedgut conjecture. So there is a small coalition that works for one of the sides, 0, 1. OK, so I'm going to try to say something, or actually maybe give you the proof. So let's start with some assumptions. So first of all, without loss of generality, I can assume that all these Bernoulli parameters are at most half. Because it's pretty symmetric with 0 and 1. They're just names, right? I put 0, 1. You can just flip one of the zeros to 1. I mean, one of the coordinates, change the role of zeros and ones. You're dealing just with a different function, but the same problem. So we can assume this. And so this is one remark. The other remark is that the coordinates which are not very biased can be handled by KKL arguments. So coordinates with probability of xi equals to 1 is, say, 1 over log n. So these can be handled using KKL. So I'm going to assume there are no such coordinates to make life simpler. Otherwise, I have to separate them, put them in a different bag, and deal with them differently. OK. This is not maybe as important here. But now I'm going to give you a definition. And the definition is a bit asymmetric. And that's because of this assumption. So let me define this. We call these boosted distributions. And that is so I'm starting with some mu, right? That's my distribution. So mu t in brackets is the following distribution. Denote the distribution of x1 or x2 xt are mu IID. So I put these super indices because I didn't want to confuse with the coordinates. So these are, each one is a vector, x superscript 1, superscript 2. Each is a vector and sampled according to mu. So mu was a distribution on 0, 1 to the n, right, on the whole cube. So I sampled t different vectors from from the cube independently, each one according to distribution mu. And I take their coordinate-wise OR. So in this new vector, a coordinate is 1 if it's 1 in at least one of these things. It's like taking the union of sets. You can also, which actually going to come up, you can think of these as sets, right? So every vector in 0, 1 to the n, you can think of it as a subset of 1 to the n, 1 to n, which corresponds to the coordinates that are 1. So I'm sampling t different sets and look at their union. So that's giving me a distribution which is a bit more likely to be 1 on a coordinate, right? Like because I sampled so many t of those. And it's a bit asymmetric, like why am I doing or? Because I assume this thing that they're at most half, like instead of and. So that's why it might seem a little bit unnatural.
And we should think of t as small or constant.
Yeah, as constant. So it's going to depend usually on epsilon, that kind of things.
Is it known how much, so the problem, I mean, this theorem is about a product distribution.
Yes.
That there's a kind of an independence
Yeah.
between the coordinates. The least little bit of dependence between the coordinates, does it automatically throw you into the counterexample kind of room?
So I haven't talked about anything non-independent, right? Even there it's independent, right? 0, 1 to the n, it's a uniform distribution. So coordinates are, yeah, right. That's a conjecture might be true. So the KKL proof really relies on independence. Because you can probably get when you have these very strong, very small correlations between variables. In this setting, actually, let me write this statement. It's actually quite interesting that. So I'm going to write another theorem which is going to imply this, that theorem. And here, there's no product distribution assumption. So let me write it. So theorem for any mu. So this is not necessarily product. On 0, 1 to the n. Let us sample S according to these boosted distributions. So S is sampled from mu to k, where k is roughly 10 log 1 over epsilon, let's say. The probability that this S is going to work, it's going to be our desired. Yes?
Mu is arbitrary, but you still assume that f is unbiased with respect to mu.
If it's biased, we already won because we just want to bias it towards 0 or 1, right?
Right, so we assume we cannot, we don't have to think about it, but in the back of our mind.
Yeah, exactly.
There
Yeah.
are trivial cases when it's unbiased.
Yeah, exactly. Yeah, when it's biased, then we are already done. So the probability that S is going to work, so in this sense, that the influence towards a value B is large, is at least epsilon for some B in 0 and 1.
So the boosted distribution was sort of asymmetric towards 1.
Yeah.
Here, the B is not going to be 1?
No. No, this is, so this is the outcome of the function, really, right? So the votes are not necessarily, the function is not monotone. So there's I should have called maybe this alphabetical, like this is like alpha and beta. So there's a difference between domain and the range, right, here. Okay, so this theorem doesn't even require independence of the coordinates. And it implies that theorem after assuming this. Because if the coordinates are very unlikely to be 1, so say 1 over log n, when you sample S from mu to the k, it's not going to have that many 1s, right? It's going to have, each one of these xi is going to have, say, n over log n of those 1s on average. And then we're sampling only constant many of those. So you're still going to have few 1s when you take it. And then there's a good chance, there's some chance that it's going to work. So it's like a probabilistic argument. So there is some S that works. And actually a random S chosen from this correct distribution, it's going to work with some good chance, like some non-trivial chance, at least.
So in particular, it's another proof of KKL.
No, well,
Oh,
if it's
because of the bias, because it's
yeah, right. This doesn't give us the original KKL. Is that if this is a uniform distribution, say, S is going to have, even just a single S sampled from mu is going to have n over 2 coordinates. And if you sample from boosted, it's going to have like many, many coordinates. So it's not going to be a small coalition. But if the coordinates are really biased, then this theorem gives us what we want. And yeah, and surprisingly, it doesn't have even independence. It requires independence. OK. So let's try to prove this. OK, so I'm going to use this notation. So I'm going to say a point x0 is good for a value b if the following holds. No, yeah, maybe it's bad notation. Should put it at the top, maybe x0. Right, it's a vector. So this is.
So, but what's the connection between mu and f in the nothing?
Well, these are all measured with mu, right? Like this influences the chance that something.
But the distribution S has nothing to do with f.
Yeah, it has nothing to do with f, exactly. Right. And it's very important for certain applications. It doesn't. Right. So maybe let me write it actually. It's just x0 and 0, 1. The n is good for a particular value b if we have the following situation. So let's look at this x0, and let's look at x0 union or with y, where y is sampled randomly. Right, so I sample according to mu. So I'm thinking of this as some upset of x0, right, like what you get. But it also comes with a distribution, which is you sample y according to mu and just take the OR. So it's good if almost everything here is b. The value of f is b here. Let's say something like this. So these are all b. So if I can manage to throw, using my coalition to throw the input into this upset or cone, whatever you want to think, it's not really a cone, then it's going to be, with a good chance, I'm going to be OK, because most things here are B. Right? So formally, if I want to write that, so good means here that the probability that, now I'm just sampling y according to mu, the probability that f x0 union y is b is at least 1 minus epsilon. OK. So now I'm going to claim that if there are a few good values for b, then we are OK. Like we can prove what we want. So let me write this as as condition 1. So this condition says that the probability that if I pick a random x, this x is good for b. So this probability is not very small. So it's at least epsilon over 2. Yes, yeah, again. So I'm sampling this according to mu. So I'm looking at this double probability, right? Like I'm sampling x from mu, then inside the goodness itself has another probability, which is sample 1. But pictorially, it looks like this, basically. So if there's some number of good points, then I'm claiming we are done. We are happy. So why is that? So the reason is, right here, if S contains a good x0, then the coalition can convert random y union y. Right, so how did we sample S? S is the union of a bunch of random points. So we picked, say, x1, x2 to xk, and we took their union as my set S. And now I'm saying that suppose S contains at least one good x0. Then take a random y. Y is coming from distribution mu, right? So the influence is that you take a random y and you want to change it by these voters in the coalition. They want to modify it so that whatever you're going to get will satisfy this thing. And the modification comes just by creating this union. They have control over x0. Those are their players, their voters. They are in the coalition, the ones of x0. So they can just convert anything that's there to 1, and then you get the 1 with high probability, right?
So this case 1 is what determines the value of k, just the existence, right? The existence of some x0 in your k point.
Exactly. So I pick enough k so that because I know there are a good number of good x0s, right? So let me write it as, so I'm thinking of S as the union of these. I'm going to use y notation here, y to k. Right, S is just like I picked many samples, like k samples, and took their union. And if there are enough good points, it is likely that one of these samples will hit one of the good points. And then automatically it's going to be a subset of S, which then will satisfy this condition. So in this case, I took this y and converted it to x0 union y. Yeah.
In the case of vector of the coalition, they can do what they want.
Even bigger. Oh, sorry. Good.
Yeah, exactly. Yeah. So they don't, like for the rest, the voters just vote, they randomly play their good role. Right, so that was a good point, actually. So let me repeat it again, that S is a coalition. So the voters in S can do whatever they want. So what I'm using from this coalition is only the coordinates in x0. The rest, just they vote randomly like the rest of the players. They act as normal non-coalition players. OK. So what if this is not the case? What if good x's are extremely rare or non-existent? Right, so what can we do now? Then what it means is that for most x0s, again, in 0, 1 to the n, the picture looks like this. When I look at this x0 union y, so for most x0s, it's not that most of these things are B. So there are quite a few other values. So I'm going to use b bar. It's like 1 minus b. So if it's 0, it's 1. So there is quite a few of these here that prevents these x0s from being good. So in this case, I'm going to say, so let me write the condition exactly. So here, probability that when I pick y, f x0 y equals b bar is larger than epsilon. So that this is not larger than 1 minus epsilon. Right, so we are in this case. So in this case, I'm going to say x0 is OK for b bar. It's not that great, but we have some b bars here. Maybe we can make use of that. So that's the term I'm going to use. But now the good thing is that it's not that we have few of these OK x0s. We have actually many of those things, right, in this case, because for most x0s, they are OK. So this statement that I wrote, being OK, is equivalent to saying that x0 is not good for the other value, original value. So these two are equivalent. So this brings us to the second case. So let's call this condition 2, which is that now when I pick a random x, the probability that x is OK for this other value, b bar, is very large. So it's at least 1 minus over epsilon 2. Because otherwise, we would be happy with this epsilon over 2. Right, so these two conditions are complementary. Either one holds or the second holds. Or OK. So in this case, why we are good? So in this case, chances are that for some yi, and yi, remember, S is sampled like this. It's the union of some y's. So for some of these yi's that we selected, f of x or yi is b bar. Right, so here it's the argument is a little bit asymmetric, which is, it looks like a slick proof to me because of that. So now what do we want to say? We want to pick a random x, which is how people are voting. We want to bias it, right? We want to change it a little bit so that the output is changed. Now I'm saying, because most x's are OK for b bar, this random x that's given to us is going to be very likely to be OK. Now that this x0 is OK, then when I pick a random y, one of these random y's in S, there is a good chance that it can convert it to b bar. So in this case, S can convert x to x or yi, which satisfies b bar. Right. So let me if you look at these two things, you see this asymmetric thing. Here, the votes that I wanted to manipulate, they were y, and then this part of S, which was good, converted it. Here, my votes are going to be OK. It's not about part of S. And then once my votes are OK, then it's random S can convert it to y bar. So there's this weird thing going on here, dichotomy.
This will happen only with constant probability over this.
Uh,
I mean, the b bar, the fraction of b bars, when you didn't, it's something like
epsilon, right?
epsilon, right?
Yeah. So I'm aiming for influence epsilon. That's how I chose the parameters. So that's why I had epsilon over 2. So epsilon with 1 minus over epsilon 2, this is OK. And then I have another epsilon over 2 elbow room to make sure that this thing is happening. So that adds up to what? All right. So that's really the proof of this theorem that we had here. Right. OK. Randomized algorithm or?
Randomized algorithm.
Yeah, you just select S from U to the T, right? Like,
Given a function, is it easy to check if a certain set S forms a biasing coalition?
I don't know, actually. OK, so all right, let me remark something. So the proof relies on this dichotomy. Either some x's are good for B, or most x's are OK for the other value, B bar. Right, so in either case we can handle it, but with a very different proof, it seems, or for a different reason, at least. So, right, so in this work, so we proved this, and it's until 12:30, or?
No, but you can talk for 10 more minutes.
OK, 10 more minutes, that's good. Right, and then there's a multi-round generalization of this thing, which is due to Russell, Mike Sachs, Russell and Pagliazzo, Mike Sachs, and Dave Zuckerman. So in the multi-round setting, the voting is as follows. So everybody votes in round 1, then you see the votes. Then you vote again in round 2, and then you vote again in round 3. So you vote k rounds, but at every round you see the previous votes. And then the outcome is related. I mean, it's a function that looks at all these casted votes in many rounds and decides. So it's a function in the multi-round. F goes from 0, 1 to n to the number of rounds to 0, 1. But that's how we think of it. So round 1, they vote. Round 2, they can see the previous votes. And now, so they proved that this KKL stuff, like the corollary to KKL, holds here too. So you can, there are functions which are, there are no functions which are really resilient. So for every function, you can find a coalition that can influence it towards one value. And that's a.
But that's not true if R is like n.
Yeah, R is a small, like log star, like that kind of, yeah, exactly. And the bounds are really bad, so it's not really similar to KKA. It's not n over log n. So log star starts to appear, but at least the little o of n coalition suffice. And the proof is a little bit more complicated. You have to show that a random set works, unlike in the KKL where you can select things recursively, saying that, OK, now I look at the next influential and so on. So once we proved this, we wanted to generalize it and show that their result also holds for arbitrary distributions. And we had some ideas. And then at some point, we realized we need some 0, 1 range is not enough to prove it. There was a nice idea which would give this, but it required that we prove the same thing for a larger range. So let's look at this larger range for a second. So now, instead of 0, 1, let me put 3 values, which will make the point. 0, 1, 2. So basically, David and Puya had a really nice idea that would give multi-round, but it required that we prove it for this. And I mean, you see this, okay, like this proof should generalize, or at least we should be able to reduce it. But the proof was so like perfectly fitted only for two-value case that it doesn't generalize that easily. So let me give you an example which shows why. Yeah, kind of very disturbing. This whole work was quite an experience for me because every step there was a new obstacle. Like anything we wanted to prove, it seemed like you had to reinvent everything, go back and reprove everything in a very different way. Right, so suppose we are in this case now. 1/3 of x's are good for, are not good, sorry, are okay for these two values, say 0 and 1. 1/3 are okay for 0 and 2. And 1/3 are okay for 1 and 2. So we can be in this case. We can easily construct a function which has this property that when you look at a random x in this set, it's like half of it is 0, half of it is 1. Another x you look at, it's like half of it is 0, half of it is 2, and so on. So there's no value that's really good in any of these sets. And on the other hand, you can't say that for most of them, say, 0 is OK. So the proof doesn't work. So this dichotomy is really about a binary case where we have 0 and 1. On the other hand, OK, so the proof doesn't work. But maybe we can reduce it to this in some way. So there is a reduction that works for the KKL setting. And that's the following. OK, so let's try to do the following. So my function is from 0, 1, n to 0 and 1 and 2. So let me put these two in the same bag and put this in another bag. So think of it as a binary case for now. So now, by the previous theorem, we know that there exists a small t, c little of n, such that t can influence either towards 0 or towards being 1 or 2, this one, right? If it can influence towards 0, take an x and convert it to something that's more likely to be 0, we are done. We managed to influence towards a particular value. But now, what about the second case? So in the second case, in the latter, so we take an x, and this t modifies it, gives us some x prime, which is likely to satisfy that f of x prime is in 1 and 2. Now we can say, OK, now we are in the 1, 2 case, binary again. Let's apply it again and find another s that can modify this to 1 or 2. So that seems like a good plan. It works for if you have unbiased variables and stuff. But there's a problem here that doesn't work. So this is the problem. If you look at this x prime, it is not true that it's sampled according to mu. Right? X prime has some weird sample because it was this x that was modified. So there's no, it doesn't tell us much that this s can pick a random x prime which is sampled according to mu and modified, because we don't know what this distribution is. So we managed to like finally prove this But that required to come up with a definition of influence which was more generalized, so which not only worked for the normal distribution, so we also look at these boosted distributions and then reprove the same thing, like go back to this proof and try to work it out for boosted distributions. So now we want to really influence X not only when it's sampled according to mu, but also sampled according to these boosted versions of it. And that changes that proof, so that proof also becomes more complicated. But once you have that, this whole thing goes through, so you can prove the constant size here, so any constant size. And then that allows us to generalize that the result of Impagliazzo, Sachs, and Zuckerman. So the multi-round also generalizes. So even with this generalized product distributions, we can prove it. OK, so that's all. You have a question? Or no? OK. Number of rounds? Or what is R?